Okay. All right, so let's begin today. So today we're going to be doing just one lesson, 2.5. We're going to be shifting functions. Here's the thing. We know how to shift functions. We'll be going with the same theme. Here's the thing, though. 1050 has a little bit, it has an additional shift of functions that we've never seen before. So it is going to have a little bit more involved with it. But it's still pretty basic. As long as you understand how shifting of functions works. Okay, so given a parent function, you can transform and move the function around with different shifts. So let's look at our first shift. If I call this red thing y equals f of x and tell you that's the parent function, then look at it transforms to blue. Isn't it being shifted up some amount of units? How many units? Each point's going up by 2. So we would write that as we're taking the function f of x and we're adding 2 units to it. Does that make sense, everyone? So that would be the up c, the plus c. And notice the sign stays the same, which we know is shifting up and down. That makes sense. Sign stays the same. So that right here, it's been shifted down 4. No, wait. Let's see. It looks like, yep, down 4 units. So you'd say we're taking f of x and we're subtracting 4. So shifts up and down, the sign stays the same. It's added on the outside of the function. We already know all that. So tell me what the shift is from the parent function. Given the parent function is x squared, what is the shift from the parent function? Up 1. Good. And absolute value of x is the parent function. That would be down 3, right? Okay, next shift is shifts left and right. Now we have it memorized and we do know this. Shifts left and right, we go opposite of the sign. So if the red thing is f of x, this function f of x, then this blue thing was shifted left 5 units. Do you agree? Sign goes opposite, so since it's in the negatives, we would call that f of x, and then it would be plus 5 because we go opposite. Now shifts left and right are grouped in with x, so notice that's why there's parentheses with the x. And then, so this one was right 3 units, so we would go opposite, so that'd be f of x minus 3. Now, here's the thing, because it's 1050, it's not 1010, you can't for the most part just memorize the rule and not understand why. You're going to be possibly asked why on tests now, okay? So you do need to maybe write down why that is. So, before we get into the whys, let's just make sure we're good with it. This would be a shift of what? Right 2. Left 3. Left 1. Now, it's actually a really simple idea of why it's shifted opposites. If you watch this example, I know it's going to click for you. So look at this line, y equals x, everybody. It starts at 0, 0. Do you agree? This point, 0, 0. Now, it was shifted right 4 units. Do you agree? Now, if I look at this, is it going to be y equals x minus 4 or y equals x plus 4? Based on our memorization, don't we know it's x minus 4? Now, here's why that is. Here's why it's the opposite sign, everybody. Look at this new xy point. It shifted from 0, 0 to 4, 0. Do you agree? So that's an xy point. Now, look, this xy point needs to be contained on either this line or this line. So which one does it work for? Well, let's plug in the xy point. Y is 0. 0 equals, isn't x 4? 4 minus 4. Is that a true statement? 0 equals 0? Yeah, so it needs to be opposite because aren't we plugging in a positive 4? Does that make sense, everybody? Because we're plugging in a positive 4 and it needs to be 0, that's going to help it cancel out. Does that kind of make sense? Look at us plug in, if it was positive 4, look at us plug in our point 4, 0. That would be 0 equals 4 plus 4. 0 equals 8? Nope, it does not. So we need it to be at the point 0, we need it to be opposite so that it becomes 0, like 0. Okay, questions on that? Awesome. Okay. Next transformation is a reflection over the x-axis and a reflection over the y-axis. Very important. Those negatives are located in different places. So if the red function y equals f of x is the parent function, if we take something and reflect it over the x-axis, what's going to happen is the negative will be in front of the function, in front of f of x. It's like negative 1 times f of x. That reflects it over the x-axis. Now let's actually make sense of why that is. So everybody look at the red function. Isn't the x values the same? Just the y values have all been times by negative 1. Yeah? Isn't it still an x value of 3? Instead of up 2, isn't it 3, negative 2? Aren't the y values just times by negative 1? Well, look, that literally says f of x is y. Doesn't that literally say take negative 1 and times it to your y values? Do you see how that literally just says to take your y values and times them by negative 1? Okay, so then what if the negative is not outside of f of x, but it's inside right in front of x? What's going to happen is it's going to reflect over the y-axis. And that one also makes sense algebraically. Look what this literally says. It says take -1 and times it to your x values. So look at the red. Look at, aren't my x values just times by -1? Instead of at +3, it's at -3. Do you guys see? So it makes sense why those are what they are. So if I say to you a reflection over the x-axis, you would times your y values by -1, right? And if it's a reflection over the y-axis, you times your x values by -1. Okay, good. So is this a reflection over the y or x-axis? X-axis. It's multiplied in front of the function. Is this a reflection over the y or x-axis? The y-axis. Because it's inside with x. If it's -1 times the original function, it's a reflection over x. If it's a negative in with x, it's a reflection over the y-axis. So what about this one? Reflects over the y-axis. What if I put a negative in front? It would also be a reflection over x as well. Do you guys see the difference? Okay. Okay, you need to write this one down too. Sorry, I know you're writing really quick here. So we're talking now vertical stretch or shrinks. We've seen these before, but now we've also just been able to say, we just said stretch or compression. We haven't been specific. We need to now be very specific. It's a vertical. You have to shift up, like it's like a vertical, meaning like y values. So a vertical stretch or vertical shrink or compression, same thing. This book uses the word shrink. It is going to affect your y values. Now that makes sense. So look at this red function, y equals f of x here. If I take and multiply in front of the y values a value, you guys see how I'm taking and timesing my y? It says take a and times it to your y values, everybody. If it's greater than 1, now the acceleration is larger, quicker. So it would stretch it up vertically like this. That would affect your y values and only your y values. So if it's greater than 1, it's a stretch. If it is less than 1, not a negative, remember the negative is a reflection over the x-axis. If it is less than 1, so basically a fraction or decimal below 1, but greater than 0, that would be a compression or shrink because you're taking it, here's its normal acceleration, the red thing, and now it's slower. So it's shrinking down. Does that make sense, everyone? Slower it's going up. So it would shrink it down vertically. You really need to remember these only affect your y values. Vertical, stretch, or compression, since it's a y thing, only affect the y values. Now here's why we have to state the word vertical. Because we've never seen before at our level until now, horizontal, horizontal, wow, I wasn't there yet, but my train of thought. We're going to have horizontal stretch and shrinks in a minute. So we'll get to there, but I just wanted to make a point of why we have to say the word vertical now, because we've never seen horizontal yet, but we'll get to it. Okay, let's go back. Got ahead of myself there. Okay, so tell me, is this a vertical stretch or shrink? Shrink, good, a shrink of 1/2. You'd say a vertical, that would affect your y values, so literally you would take your y values and times them by 1/2. Does that make sense, everyone? Okay, right here, this would be a vertical stretch of 3. This would be a vertical stretch of 5/2 because that decimal is larger than 1. Okay, so let's put all of those together to make sure we're good. All together, can you state the shifts so far? So just right here, I'm asking you to tell me what the parent function is. So take up all the shifts. Wouldn't my parent function be absolute value of x? Then as I point, tell me the shift. Right 2, up 5. Great, and we have to say vertical stretch by 3. Because we're going to have horizontal stretches and compressions in a minute. Okay, awesome. Now right here, this one's parent function would be x squared, y equals x squared. So then this is a reflection over the x-axis, a horizontal, no, I said horizontal, but it's not. It's vertical shrink of 1/2, correct? And then it would be down 3 units. Okay, good. What would my parent function be here? Square root of x, okay, right here. Reflection over the x-axis. Vertical stretch of 2. Left 1, down 5. Now, it's always interesting when people see this and then they say, well, what about that -2 in front? And they, like, freak out. How can I rewrite it?
On the end.
On the end. Isn't that just, like, subtracting 2 in front, everyone? Yes. Is 3 plus 2 any different than 2 plus 3? No. So, reorder it. That's -1/2 x plus 1 squared minus 2. So, then you would say, reflection over the x-axis, a vertical shrink of 1/2, left 1 down 2 units. Everybody good? Okay, I'm going to throw a wrench in it. Here's an important thing to note, everyone. I'm going to give you a new function here. If I said to you, what's the shift of this, you would say a reflection over the y-axis. Now, here's what people get messed up on. Because of the plus, they say left 1. That's what we normally do, right? But here's the thing. This negative has actually been distributed. Meaning, if we have a negative in front, isn't it more appropriate to factor it out? Yeah. Divide by -1, divide by -1. So that's actually this, x minus 1 squared. -1x minus 1 squared minus 2. So you'd say a reflection over the y-axis, but it is right 1. Does everybody see? You have to be really careful with that. Don't mess up on that. And then down 2 units. So if you have the negative in front here, factor it out. There's your shift left and right. Awesome. Thank you. Okay, writing this one down. Now, we've only ever seen before in our level vertical stretch or compression. Now we're going to be doing, that's a y shift. It's taking your y values and going up or slower. Now we're going to be talking horizontal x value stretches or shrinks. Okay, so I'm writing this one down. So y equals f of x would be my parent function, this red thing. Now, isn't the pink thing horizontally shrinked? And the blue thing is horizontally stretched out. So something really interesting happens with this. So what's happening is, before when it was vertical, the a value was multiplied in front of the function. Now notice the a value or c value, we're just using a different variable, is times right in front of x. That's going to affect your x values. Do you see how it's times right in front of x? So if c is greater than 1, it is opposite of what vertical is. So if c is greater than 1, it's actually a horizontal shrink of 1 over c. Do you see how that's opposite? Normally we call that a stretch. She's not here today. So writing that down. So everybody, if you see this, y equals f of 2x, this is not a stretch of 2. It's a shrink of, it's a horizontal shrink of 1/2. Do you see how we flipped it? I'll explain why in just a second. So if we're looking at this, this would be the pink function here, okay? This would be the equation of the pink function. Okay, let's do, looking at this, if c is below 1, not negative, the negative is a reflection over y, but if it's a decimal or fraction smaller than 1, it's actually a stretch of c. So right here, if we have y equals f of 1/2 x, this would be a horizontal stretch of 2. Do you see how I just flip them? Either way, it's opposite with horizontal. Okay, now here is, hopefully this might help some people understand, well, why is that? So let's focus on blue. Right here, blue, let's say that it was this equation, 1/2 x. Okay, that is creating blue. Now here's y. Okay, look at red. To get from point A to B, let's say just to get from 0, 0, A to B, then to the blue, this would be A to B, right? Look, from A to B of the original, now from A to B to the new thing, isn't it taking twice as long to cover the same amount of points? So do you see how it's taking twice as long? So that's why it's the opposite.
It's also like if the x of 1/2 equals 0. That union thing or am I just making it?
No, that's a great question. Say that one more time.
So like the 1/2 x equals to 0, then you multiply it by 2, right? So it's just x equals 2. And then it's
Oh yeah, good point. Yeah.
so it kind of makes sense.
Yeah. Yeah. Awesome. Okay, so I was just hoping that maybe that would make a connection for you. Okay, awesome. So let's go through, if you want want to write these ones down, this will kind of maybe be something good to refer back to. So maybe write at least just this top one down. So let's go through and verbally describe the transformation and then make sure we understand what it's going to affect, either your x values or your y values. Alright, so y equals negative 2 times 3x squared plus 1. The parent function would be x squared. Then our negative is a reflection over the x. Doesn't that affect your y values? Yes. Okay, just a reminder. This is a vertical stretch of 2. Now this is a horizontal what? Shrink of a third. Okay, good. And then up 1. So then the stretch of 2 will affect your y values. This will affect your y values. Horizontal affects your x values. Up 1 would also affect your y values. Just making sure we understand what each thing's affecting. Questions on that? Okay. You sure? Okay, let's do another one. Alright, so now just verbally state, this would be a vertical shrink of a half or compression of a half. Correct. This would be a horizontal stretch of 3 down 4. This would affect your y values. This would affect your x, and this would affect your y's. Okay, good. All right. Let's see if we're going to get tricked on this one. A reflection over x, vertical stretch of 5, reflection over the y-axis. It's left 2, isn't it? We have to pretend, right? We have to factor out the negative. If we do, won't that actually be positive? So left 2. And then up a half. Okay, good. Okay, right here, reflection over x, a vertical shrink of a 4, and then isn't this a horizontal stretch of 2, everybody? Isn't 0.5 1/2? Okay, then it would be a horizontal stretch of 2. Okay, awesome. I think we get it. Okay, let's use that to now be able to graph. Okay, you're going to be asked to, given this graph, perform the transformation. Now, obviously, guys, if it's just a shift left and right, up and down, it's easier to just take it and literally say, okay, I'm going to take each point and shift it right 2, up 1, and just move them all, right? Just move them all, but the thing is, they're not all going to be that straightforward. There's going to be some with extremely advanced shifting. So I think you should just go with the theme that we've done all year long, which is write down the parent functions x, y points, and then shift them based on this shift. So let's write down some important points over so that I can recreate this graph. Negative 5, 0, over negative 3 up 2, this is the parent function, over negative 2 up 0, and then over negative 1 down 4. Now that's the order that they connect, agreed? Okay, so now inwards we would just describe the shift. We'd say right 2, up 1. So then our shift right 2 is an x shift, so we'll add 2 to our x's, and then up 1 we'll add 1 to our y's. You'd write down the new x, y points and graph them. So negative 5 plus 2 is negative 3, negative 3 plus 2 is negative 1, negative 2 plus 2 is 0, negative 1 plus 2 is 1, 0 plus 1 is 1, 2 plus 1 is 3, 1, negative 4 plus 1 is negative 3. Do you agree? Then just plot those points, and then we kept them in order, connect them in that order. So negative 3 up 1 unit will then connect from negative 1 up to 3. Then it will connect from 0 up 1. And then will be from over 1 down 3 units. And you see how it's just been shifted now. We've done this though, right? 10 times? Okay. Let's do one with a lot more involved, because you have to order matters in which you apply the transformations. So I'm going to write down the transformations. Reflect over the x-axis. Then after that, we have a vertical stretch of 2. Then we have a left 1. And we have an up 3. Now let's determine which values it's going to affect. Reflection over x affects your y values. Do you agree? Vertical stretches affect affect your y values, left 1 will affect your x's, and up 3 will affect your y's. Now look, there's 3 things that are happening. They're all affecting y's. Order matters. Now if you think about it, the first thing we would do is, if we're reflecting over x and it's a vertical stretch of 2, we're going to be timesing our y values by, let's just hit 2 birds with 1 stone, -2. You guys see? But then after that, we're going to add 3. Multiplication comes first. So you got to do the multiplication part first. Very important. So we'll times our y values by -2, then after that we'll add 3. And then our x values are shifting left 1, so we'll subtract 1. And now we'll just write down our official new x, y points. -5 minus 1 is -6, right? -3 minus 1 is -4, -2 minus 1 is -3, -1 minus 1 is -2, 0. Now, 0 times -2 is 0, plus 3 is 3. 2 times -2 is -4, -4 plus 3 is -1, 0 we've already done, it's 3. -4 times -2 is 8, 8 plus 3 is 11. Connect them in that order. So -6 up 3 units is my first point, which will connect to -4 down 1 unit. And then -3 up 3 units. And then over -2 up 11 units. It should have the same shape, does it? Yeah, it's just been reflected, stretched, and whatnot. All good? Okay. Okay, awesome. We don't have to do this one if you don't want. I just want to make sure that we would know which values get affected by which thing. So this is a vertical shrink of a half, correct? Then we have a reflect over the y-axis, and we also have a down 4. So vertical shrinks affect y's, don't they? Reflection over the y-axis would affect your x's. Down 4 would affect your y's, wouldn't they? So if we're reflecting over the y-axis, we're going to take and times our x values by -1. Then our shrink will times our y values by 1/2. And then after that, won't we subtract 4? And then you'll write down the new x, y points, graph it. Do you need me to do that part, or is the hard part done now? You can do decimals, you know. Decimals are easier to plot points with sometimes. Hey, last one, a reflection over x, correct? That's a y shift. And then this is a horizontal shrink of 1/2. Guess what? That affects your x values, doesn't it? Horizontal. So you're going to take your x values, times them by 1/2. Then after that, a reflection over the y. So then after that, can't I times them by -1? Times by -1. So technically, let's just times it by -1/2. And then there's your new points. Okay, awesome. We're actually almost done with the lesson now. This is the last thing. All right, even and odd functions. Write this down. Very important. So even functions will have, what makes something an even function is, if you're given a graph of a function, it will be even if it is symmetric or has symmetry over the y-axis. Meaning if I was to look at the blue, the right side of the blue, and stamp it across the y-axis, if those are perfect images of each other, it would be even. I had to freehand them, so I didn't do very good. Pretend like those are perfect mirror images of each other. Just focusing on the graphs right now, not this f of x part stuff. So right here, do you see how if I take this line and if I stamp it across, pretending like I drew it perfectly, it would be a reflection over the y-axis. That would make it even. So that's the first thing you should know. If you're given a graph, if it is a symmetric over the y-axis, it's even. Odd functions have symmetry over the y, then x-axis. That does say y. It's just covered by the yellow thing. So it has a symmetry over the y, then x. You've got to flip it over both. And honestly, you can flip it over x and y. It doesn't matter. So look, this would be considered odd. Here's why. If you reflect it over the y-axis, wouldn't it look like this? Then reflect it over the x-axis. Does it end up in the right spot? Yeah, so it would make it odd. Right here, reflecting over the y would put it like this. If I reflect it then over the x, does it put it in the correct spot where it should be? Yes, so that's what makes it odd. So just focusing on graphs right now. Now there are functions that are neither. If they don't reflect over the y-axis and are symmetric, and then if they don't reflect over y then x perfectly, if that's not a mirror image, then it's neither. So look at these three graphs, graph A, B, and C. Would graph A be even, odd, or neither? Odd, because if I reflect over y then x, it's a mirror image. Now how about graph B? It's neither. If I reflected over y, wouldn't it need to look like a W? Right? And if it was odd, then it would need to reflect over the x-axis, so it would not look like that. So this one's neither. How about graph C? Even. Okay, good. Now here's the thing though, we are not going to be given graphing calculators, so you're not going to be able to use graphs all the time. They could give you a graph on the test and ask that, but also, for most likely, I guarantee, they're going to have, I would say, they'll at least have one. I think they'll probably have two where you have to use algebra, so write this down. So here's how we can use algebra to determine if something is even, odd, or neither. What you do is you take the original function, okay? And what we're going to do is we are going to plug in negative x. This is always what we plug in to test if something is even, odd, or neither. We're going to plug in negative x into the function. We're going to do some math, calculate when we plug in negative x, simplify it down, and then we're going to look at our answer. If our answer is equal to the original function f of x, if they're exactly the same thing, once you plug in negative x, it simplifies to be the exact same thing as the original f of x, it's considered even. Everybody good with that? Okay, now here's how you test if it's odd. Same thing, you take the function, you plug in negative x, so we always plug in negative x to test it. And if you do this simplification and you look at your answer and it comes out to be negative 1 times the original f of x, that would make it odd. So if you look at it and you say, well, that's negative 1 times the original, it's odd. If it's not either, if it's not the original and it's not negative 1 times the original, it's neither. You're going to see a couple examples. It's actually really straightforward as long as you can do algebra and really simplify things correctly. And then use your brain to compare. Do you have those written down? So if I say to you, is this even, odd, or neither, what do you do? Plug in a negative x. Okay, well, here's my first example. Even, odd, or neither. So you'd say, okay, I need to plug in negative x and then do some math, algebra here to simplify. When we plug in something, we've got to use parentheses. So this would be negative x to the 5th plus negative x. Now what you're going to do is simplify it down, and then we'll compare it to the original. Now everyone remember, this is really negative 1 times x to the 5th, isn't it? And then we have plus negative 1x, don't we? So then a negative to an odd degree is going to stay negative, isn't it? Yeah. So we have a negative x to the 5th. We've just simplified that. Plus a negative is a minus. So isn't that as simplified as it gets for the most part? Yes. Now is that the original? No, there's negatives. That didn't even have a negative. You guys see how it is not the original function? Okay? So then what I would do is say, okay, is it negative 1 times the original? Well, first of all, to compare that, isn't it true that you shouldn't have a negative in front, technically? So can't I factor out negative 1? Divide by negative 1. Divide by negative 1. So then left would have been x to the 5th plus x, isn't it? So now compare it. Is it negative 1 times the exact original? Yes. So it's odd. So pretend it would have, let's say we would have factored out a negative 1, let's pretend, and what if it would have been x to the 5th minus x? It'd be neither, because it's not negative 1 times the exact original. Do you guys see? The sign was not right. Okay, let's do another one. Even, odd, or neither. Here we go. So you'd say to test this, I plug in a negative x. So using parentheses, 1 minus negative x to the 4th. This negative doesn't get put in, so guys, 1 minus, nothing can happen with that, right? Now this is negative 1x to the 4th. Isn't a negative to the 4th power positive? So then we have 1 minus x to the 4th. Isn't that as simplified as it gets? Yes. Is it the exact same as the original? Yes, so it's even. Now notice I like to always compare things in the same order, so I left it. Does that make sense? But if this would have been ordered differently. I always like to compare them in the exact same order. Okay, another one, even, odd, or neither. So you'd say plug in negative x. So that'd be 2 times negative x minus negative x squared. So this is negative 2x, isn't it? This minus sign can't be changed for a second. And then a negative squared is positive. So we have minus x squared, don't we? So is it the original? No. Is it if we factor out a negative 1, divide by negative 1, divide by negative 1, left would be 2x plus x squared? Is it negative 1 times the exact original? No, because the sign's wrong. So it's neither. You're right. Last example of the day is this one. Even, odd, or neither. Even, odd, or neither. Let's see. I plug in a negative x. So we have the cube root of negative x minus 2 times negative x. I always have people get so hung up on this. Isn't this the cube root of negative 1 times x? And then this is a minus a negative, isn't it? So plus 2x. Now, the cube root of negative 1 is negative 1. So we pull out the negative 1, don't we? We can't pull out the x, can we? So we have negative 1, cube roots of x, plus 2x. Is it the original? No. Let's pull out the negative 1, divide by negative 1, divide by negative 1. So then left is the cube root of x minus 2x. Is it negative 1 times the original? Yes. So it's even. Odd. Odd indeed. Okay, awesome. Good catch. All right, homework time. Okay, the ones that are the even, odd ones, if you want to practice those first, that's these ones. You need to be doing all, evens and odds, because otherwise you don't have enough practice to be successful on the exam. So 75 through 82, those are the even, odd, or neither ones. I would do those first.